Okay, well, turns out that I ran out of storage there, so hopefully this will be nicely merged together once I get it online. But what we were saying here was that the probability of having 5 or more cases under this assumption was very, very low, and so that would give us reason to suspect that the rate had gone up. On the other hand, if this probability had worked out to be something like 0.2, then this would be something we would expect to see once out of every 5 years, and something like that is not something that's typically rare and wouldn't give us any reason to suspect that the E. coli infection rate had gone up in this area. Okay, well, last but not least, literally with the poisson, we've got the mean and the variance. Again, we'll go through the derivation of the mean. The derivation of the variance is left up to you as far as one of the homework problems. So, although I'll certainly give you what it works out to be. So, the expected value of x, we've got the sum, x equals 0 to infinity, of x times lambda to the x e to the negative lambda divided by x factorial. Now, this one's starting to look a little bit like the binomial, and when you do the expected value of x squared, you're going to use a similar type of technique as we used when we did the binomial. So first off, we'll note that when x is 0, this term is equal to 0, so we can actually start this summation at x equals 1. And then, as we did in the case of the binomial, we can go ahead and cancel the x with the x and the x factorial. And so what we have now is the sum x equals 1 to infinity of lambda to the x e to the negative lambda over x minus 1 factorial. Now, if you remember from the binomial, one of the things that we did was we paid attention to the relationship we had here, in the case of the binomial, to make sure that we have something set up so that it sums to 1. And the things that we need in this case, the base here has to be the same as the opposite of the exponent up here. We're working with the natural base. And then the exponent here has to be the same as the argument here. We need to sum from 0 to infinity. So in this case, we've got x here, we've got x minus 1 right there. The lambdas match up. So in order to get these the same, what we'll do is factor out a lambda. And since it's just lambda, it's not a function of x, we can pull that outside the summation. And we've got the sum x equals 1 to infinity of lambda to the x minus 1 e to the negative lambda, all divided by x minus 1 factorial. So we have the matchups that we need. The last thing we need is for this summation to go from 0 to infinity. And again, like the binomial, if you take a look, really what this is doing is going from 0 to infinity, because when we start with x equals 1, this becomes 0, this becomes lambda to the 0, x equals 2, this is 1, that's 1. So just like the binomial, we need to change a variable. We're going to let w equal x minus 1. And then this summation becomes lambda times the sum w equals 0 to infinity. Lambda to the w, e to the negative lambda, divided by w factorial. All of this is 1. And so the mean is lambda, which should make sense because lambda is the rate at which things occur. In this situation, remember lambda was also defined to be n times p when we were doing the buildup of this from the binomial, and n times p is the mean for a binomial distribution. So the expected value of the mean of a Poisson is lambda. However, for the variance, it also turns out that the variance is lambda. This is the only distribution for which, or at least common distribution, for which the mean and the variance are always equal to each other. We will cover distributions where the mean and the variance can be equal to each other, but they're not guaranteed to be, except in this scenario. So one of the things for people who've taken Stat 1 and or have seen some data analysis, one of the ways to take a look at a discrete random variable and try to determine if a Poisson distribution is a good way to go to start, and this is going to be part of one of your take-home things, is to take a look at the mean and the variance for your data set. And if it turns out that for this discrete random variable, the mean and the variance are very, very close to one another, then a Poisson model might be a good one to look at to start with. So anyway, like I said, the Poisson is the only distribution for which this holds. And this ends section 3.8. So if you've done this video last, then this is the end of the named discrete random variables. This is the end of the videos for this week, and you can work on the homework. By all means, if you need help, go over to Robinson to talk to some of the professors who were willing to handle some questions for me this week. And have a good weekend, and I'll see you back following week.